Good afternoon, everyone.
Good afternoon, ma'am.
So, what we discussed in the last class? What is the structure of a given assembly program? And we have discussed about assembling and running an 8051 microcontroller. Okay. So, what are the different steps involved while running an assembly programming? What are the different steps? Anyone? What are the different steps involved in writing an assembly program? Yes.
Editor program.
Editor program. Then
Assembler program.
assembler program. Then
Linker program.
linker program. And the last one
Object
is
hexadecimal.
OH program.
OH program.
So first, what do you mean by editor program? What is an editor program? Here the programmer used to write the program in any Microsoft team. Okay, field either you can use MS, DOS or any notepads to write the given assembly program. I mean, you are going to write the instructions in the editor. So once the program is typed in the editor window, so next we have to save. So what is the extension to save this particular file? Yes. What is the extension? My file dot SASM, or sometimes you can use my file. I mean, some particular Windows will use my file dot src. Src represents a source code. So these are the very first step in case of editor window. The program will be saved with an extension of your file dot asm. You can give any file name with respect to given program. Next, in the assembler program, you're going to the editor, after writing the program in the editor, you're going to save in the assembler. So here in the assembler, where instructions will be converted into machine codes, and it creates a file called, one is object file and one is list file. So my file dot, what is this? Obj, that is object file, and my file dot lst, I mean list file. So object file will consisting of the machine codes which are generated from the editor to assembler programming, where in the list file it lists all the operands, and as well as it lists all the particular address, followed by, if you have any error in the program, those syntax error will be listed in the list file. So this will be very useful for the programmer to identify the errors and as well as to identify the different address and operands in the given program. Then the linker program is nothing but it will collect two or more object files, or it will combine two or more object file, and it creates an absolute file, that is called my file dot abs. It creates an absolute file. So once the absolute file is created, the next step is OH program. You are going to convert your absolute object file into an exa file. Finally, it creates the last file, that is called my file dot your hexa, hex. So all these hexadecimal converted code will be burned into ROM, and your program is ready to execute. Okay, so this is how you're assembling and running a given 8051 program. Okay, any doubts here? Do you have any doubts? So next, once we know about this assembling and programming of a given 8051 program, the next is we are going to write Sorry, we are going to study about the assembly directive. In the yesterday's class, we have discussed about the data type. What is the data type? We have only one data type, that is 8-bit data, right? So we are going to define any 8-bit. Yes. So any 8-bit data with the help of DB. So what do you mean by DB? It is define byte. Okay. So can you give example for this? So you can define any decimal or any hexadecimal or any ASCII codes. What do you mean by ASCII codes? What ASCII represents?
American Standard Coding
Code
of Information.
for information interchange. So you can define all the capital uppercase letters from A to Z and lowercase letters from A to Z along with that. So all the numbers you can define using ASCII numbers, but it should be single quotes or double quotes. Okay. So here the numbers will start from 30. 30 is nothing but 0, 1, 2, 3 like that. So number starts from 30. Okay. So here some particular monitors or keyboards or some particular system will convert your hexadecimal or decimal numbers into an ASCII. It depends on how exactly the system is designed. Okay, can you give one example for DB? Data 1. This is a label. This is the format for defining a byte. Okay, DB. Okay, I'm going to define 20H. Now it is in hexadecimal. So similarly, I'm going to define data 2. You can define byte and give binary numbers. We will represent B represents a binary number. So here if you did not represent H, it means it is a decimal number. So if I represent H, it is an hexadecimal number. So you have only one data type, that is 8-bit data type. So that can be defined by using your DB. Only one particular data type. So now we have to, once we know about the data type, the next one is directives. So here the assembly directives are nothing but these are called pseudo codes. So these pseudo codes are org, origin, then EQU, equate, and third one is END, I mean end. Okay, so these are the pseudo codes. So we have some codes. Okay, I'll show you. I have explained in the last class about your move instruction and add instruction. Okay, move and add instruction. So these instructions are, okay, these are directives to CPU. These are directives to CPU. It tells CPU what action to be done. I mean, move means what it will do? It will just copy the source value to destination. Add means what it will do? It will just add the source value with the destination value, I mean accumulator. Okay. So here these are directives to the CPU. Okay, it will tell some actions to do for particularly CPU. But these are called directives. So these directives are to the CPU. But these directives are called pseudo codes. These are codes, but these are pseudo codes. Means these instructions are not to the CPU. These are to the assembler. These are assembler. For what? To start the program. ORG is for to start the program and end is to stop the program. And EQU is nothing but to load a constant value. Clear? So later I will explain. Initially these are pseudo codes. These are directives to the assembler but not to the CPU. Okay. Hence these are called pseudo codes and it will tell that we have to do these actions. What are the actions? To start the program, I need to start with ORG. To end the program, we need to end. Okay. So these are the directives to the particular assemblers but not CPU. For what? So to start the program, to end the program, sometimes we have to load some constant value. So under those conditions, you need to use EQU. Okay. So first I'll explain about your ORG. The pseudocodes are directives to the assembler in order to start and in order to stop the given program. Okay. So now ORG, this is the origin. So here in order to, the assembler, okay, has to understood that. So initially for any particular program, we have to start with ORG, means this is the origin of the given program. So now along with this ORG, we need to specify from where exactly we are going to start from the memory location. So now ORG 000H. What is the meaning of this? I am going to start with the 0, starting value from the memory location, or you can write ORG 00001H or ORG 056H. 56th location in the memory or the first location in the memory. So 0th location of the memory. So we have to specify from where we have to start our program, and we have to specify the memory location from where we are going to start the program. So from that, your all the codes values will be started loading there. Okay. So we are going to store those values or those information from the location 0. Or sometimes you are going to specify, I need to start with this particular address location or this particular address location. Then you need to specify the address location. Okay, this is the start of the beginning of the program from where you are going to start your program. Okay, any doubts here? Some assembler also uses .org. Either you can use .org or .org 00. Okay, so either you can use this format to begin the program or this format. It all depends on which particular assembler you are using. Usually we are going to start with this one, ORG or with particular address location. So now I will write on program structure how we are going to start your program. Okay, so I will start with ORG 000H. Okay, I'm going to write move. Okay, move R1 hash #. Then move A, move R2 hash #. Then move. Okay. Or I can also write, I need to add these two values. Then you can just write and A, okay. So after this, I'm going to end your program. Just end. So now you can notice that in order to begin your program, you have to start with ORG, that is origin. This is the directive or instruction to the assembler, but not CPU. These are the instructions to the assembler. So what about this particular structure? Here, these are directives to the CPU. It will tell CPU what to do. What is the action? I need to load an immediate value of 30H to the R1. Now I am storing that 30H to accumulator, R1 to accumulator. Then I am loading 20H value to R2. Now what I am doing? I am adding A. A is having 30H and R2 is having 20H. Now I am going to add these two values. So now I will come on this particular instruction. So this is end directive. So what is the use of this? So this is an instruction to the assembler. This is an instruction to the assembler. For what? Now I am going to end this program. What I am doing? I am going to end this program. If you write any instruction after this end command, it will not execute it. Clear? Should be very clear that if you write any opcodes or any mnemonics or any particular instruction after this end, it will not execute. The assembler will not, or the CPU will not consider these particular instruction. Hence, once the program is finished, you are going to end the program with END. Clear? So this is what the general structure of the given assembly programming. So first you have to start with the assembly directive, org, with the beginning address. Then write your program. Once the program is finished, then you are going to end the program. So if you write any instruction after this end command, this will not be considered. Okay. So this is to end the program. If you write any particular instruction below this, it will not be considered. Clear? So this is about your end directive. Any doubts here? This is the general structure of a given assembly programming. So first you have to start with org. So when you start writing the program with respect to in the computer, or when you want to execute this program, if you write only this much, the assembler will not consider. You have to start with org with particular memory location, and you have to end the particular program with end directive. And one more is EQU. This is equate. So what is this particular directive? So this is also a pseudo code. This particular instruction is not to the CPU. This instruction is for the assembler, and sometimes you can also use it as a given code in order to load a particular value. Sometimes if I want to load a constant value, let it be assumed that 55 is a constant value. I need to load this value in the, or I need to use this particular value in the program. So under those conditions, you just use this 55H, or you just load this 55H to the EQU, so that you can able to retrieve the same particular value without changing. Okay, without changing its original value, you can able to load this particular value. So now one example. So I'm going to use one label, count, or you can give any particular label, count EQU 55. Now this is the constant value. So somewhere here we have some instruction. Somewhere I want to load this particular value. So just you need to use move. I'm taking one register R3, hash count. Notice this symbol. This represents we are loading a value to the R3 register count. Because count is assigned with the constant value 55 with EQU directive. Okay. So now you can retrieve this 55 value by writing move R3 hash count. Clear? So now after execution of this instruction, R3 will be loaded with the value 55. Now you can ask, what is the advantage of using EQU? Because during execution of a long program or a long task, under those conditions, this constant value will be changing throughout the program, and somewhere we require a original value of this particular constant value. Under that condition, here if I not use this EQU instruction, the programmer or the assembler will be spending lot of machine cycles and lot of time by retrieving this particular value, because throughout the program this value will be changing. For example, I am adding a plus this value, later I am taking this value and I am adding again 13h. So throughout this program this value will be changed. During next cycle I want the same particular value. Under those conditions, just you write move R3 hash count, the original value will be loaded to R3 register. So without changing its original value. Clear? Sometimes in the programs we will be having some constant values. So under those conditions, the constant value will be loaded to EQU. Clear?
Ma'am, if we write that hash symbol, the count will be executed, ma'am.
No, what happens, if you write this hash symbol, meaning that the count is assigned with the value 55. So 55 will be loaded to R3. This is the name we are giving to this particular command. So when you load this particular count, this particular value will be loaded to R3. You can change any constant value, 25. Now R3 will be 25. Not only count, you can give any name, you can give your name also. So this is just a label. Okay, this label when you call in the program using this hash symbol, so then the value will be loaded.
Yes, ma'am.
Okay, clear? So next I'll start with instruction sets. First one is, the first type of instruction is arithmetic instruction set. In that, first we have addition, okay. Here we will be having three types of addition. Addition, for simply addition you are going to use ADD, okay. Then ADDC. C represents addition with carry. So when you write ADDC, you are adding with the carry. And we have DAA. So there are three types of addition. The first one is general addition. So this is addition here, addition with carry. This will be used when you are using BCD addition. When you are using BCD addition, then you can go for DAA. So I'll explain one by one. So first I'll consider this one. Okay. Can you tell me what is the format for addition instruction? What is the syntax or what is the format for addition instruction? So first I will consider unsigned addition. So what is the format? It is add, okay, a comma source. Usually the destination. As I told you, in addition, the destination is always accumulator. So after execution of this instruction, in the comment part, A will be having A plus source. You are going to add whatever the value in the destination along with source. A is equal to A plus source value. So we will be having a different pattern for addition. Add A comma hash n. Meaning that you can add A, and immediate value. What is the meaning of this? You can add accumulator with n represent any value, 1, 2, 3, 4, 5, 6, 20, 30, 40, whatever it may be, but you are loading an immediate value to accumulator. So this is the first format. Okay, the accumulator will be added with any immediate value. So then add A comma R. So here add A and registered value. That R, this small r represents 1 to 7. Any register, either it may be R1, R2, sorry, 0. R0, R1, R2, R3, R4, R5. Meaning that you can add any value to accumulator that may be from the different register. R1, R2, R3, R4 up to R7. This is the second pattern. We can add A comma your address. Okay. Add A and okay memory location address. Understood? Okay, this address, okay, this ADD represents address, or you can also write memory address. MR represents it is a memory address. I'll write examples also. Means you can write add A comma 17H. Now whatever the value which is stored in the 70H will be added to accumulator. And there is one more possible, add A comma at RI. Means that add A and okay any RI register. This I represents 0 and 1. Indirect addressing mode. Okay, indirectly you are specifying the address. So, but for indirect addressing modes, only we have a rule that only you can use either R0 or R1 register. You can't use R2 and R7. For indirect addressing mode, only you can specify register 0, R0 and R1. Clear? So now you can see the examples. Okay, see, move A comma hash 30H and add A comma okay hash 30H. Now after executing this instruction, A is equal to A plus 20. A is how much? 30H plus 20H. Understood? This is the example for first one. Add A comma hash 30H. So you're going to use an immediate addressing mode, and you're going to write you're going to load an immediate value okay to the accumulator. You can notice that the destination is always an accumulator, but the source value may be any immediate value, any register, any memory location, or any indirect address location. Clear now? First example is clear. The next one is, next I will write one more example. Second example, move A comma hash 32H, okay, add A comma move R3 comma hash 40H, okay, then move 32H and okay, A comma R3. Understood? So now here A will be loaded with 30H, 32H, then R3 will be loaded with 40H. Now A will be having a value of 32H, and R3 will be loaded with the value 40H, and we have added A and as well as R3. This is the example for second type. Clear now? Do you have any doubts? Now I will write example for third one. I am using now a memory location. Okay. Move A comma hash 30H. Okay. Directly you can write add A comma write any address location. Clear now? I'm loading a value 30 to accumulator. Now accumulator will be loaded with 30H and we have some value in 20H register. For example, okay, now this 30H will be added with 32H. After execution of this result, A will be having a value of 30 plus 32. Final will be 22 plus. Note down this example for each type of addition. Note down the examples. Clear? Do you have any doubts here? Now I will give example for fourth one. Have you copied this? Say yes or no. Finished copying?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Any doubts? Move A, 30H. Now I need to use indirect addressing mode. So when you are using indirect addressing mode, first I need to specify which address it is, for which particular register which address is allocated. Listen here. Now move A, 30H. A is going to be 30H. Now move. Okay. So when you are specifying this RI, either you can use R0 or R1 register. Move R1, okay, 30H location. I have loaded with 30H location. So now you can add A, okay, here R1. So whatever the value in 30H will be loaded for this R0. Sorry, move A, should use at R1. Now whatever the content in 30H, now 30H will be having the value of 10H. So what happens? A is equal to 30 plus 10H. So this 30H is allocated to R0. So similarly, when you increment this one R0, then it will be 31H. When you increment, it will be 31H, like that. So the advantage of using indirect addressing mode is you are specifying an address particular memory location to one particular register. So for next subsequent addition, you just increment the memory location, you can able to get the different location 31H. Now 31H will be having the value of 9. 32H will be having the value of 40. Like this. So that particular value will be loaded. Now whatever the content in 30H location will be added to accumulator, but this location is allocated to your particular register, either R0. You can use, instead of R0, you can use R1, but you cannot go for R2 to R7 registers. Should be careful when you are using indirect addressing mode. Either you can use R0 or R1. You can't go for any registers from R2 to R7. Clear? This is about one simple different examples for each type of instruction type. You can add an immediate value, you can add with a register any value which are loaded to register, you can use any memory location values which are stored in memory location, not the memory location address, the values which are stored in memory location. The difference is whenever it is this particular count symbol, meaning that you are going to load in an immediate value, and this is for indirect values from the particular memory location. So now I'll show one particular example for addition. Note down. First you copy this. So yesterday someone asked, so how we are going to use different addressing mode. So this is how we are going to use different addressing mode with the addition instruction. Now I will show one example. So note down, show how the flag register is affected So how the flag register is affected for the following program. So here I am not writing org because when you write the program in the editor window, you have to start with org. Now it is not required in the board, so I am not writing org. A comma hash 0 F5H, then add A comma hash 0H. Now here A will be loaded with the value 0F5H. Here A will be added with A plus 0H. I mean 0F5H plus 0B. I need to show how the flags will be affected with respect to which register? PSW register. Program status word. See, listen. So if you just write move A comma hash F5H, the assembler will show an error because when you writing these A to F letters, okay, it will be considered as a particular alphabets. Hence, in order to avoid that, you are going to use 0. When you are writing a particular letters from A to F, you should be careful that you have to use 0 in front of those letters. Otherwise, the assembler will be considered as normally a letter, but not A to F values. So now I need to add these two values. First, F5. Okay. 1 1 1. Yes. 5 is 0 1 5. Then 0B 0 0 0. B value is 1 0 1 1. I need to add these two values. 1 plus 1 0 carry 1 0 carry 1, 0, carry 1, 0, carry 1, okay, then 0, carry 1, 0, carry 1, 0, carry 1, then 0, carry out, carry 1. What is the answer? Answer is 0, 0. Now, it should be noticed that this is D7 bit, D6, D5, D4, D3, D2, D1 and D0. So now you can see that these are the starting 4 numbers. I mean, these are called the first set of nibble and these are the second set of nibble. There is a carry out from D3 to D4. There is a carry out from D3 to D4. This is called an auxiliary carry. This is called an auxiliary carry. Auxiliary carry. There is an auxiliary carry, right? There is a carry from D3 to D4. So, auxiliary carry is 1. So, there is a carry from D7 bit. There is a carry out from D7 bit. Hence, it is a carry. Carry is 1. So, now you can see that is there any all the values in the given answer is 0, 0, 0. Hence, it is an even parity. When it is an even parity, P is equal to 0. Since we are performing addition, we don't have any overflow here. Okay. Now, I'll consider the PSW register. Okay. In the PSW register. So, what are the PSW registers means? Carry, auxiliary carry, this is carry, auxiliary carry, this is F0 we are not using, RS1, RS0, overflow, this bit we are not using, and finally carry bit. Right, this is what a PSW register. As I told you, when you are using an arithmetic operation, there are some carry or there are some flags in the PSW register. Those flags will be affected when you perform an addition. So there is a carry, right? So yes or no? There is a carry. Hence, this flag will be raised. Is there any auxiliary carry? Yes, there is an auxiliary carry from D3 to D4. So 1. So we are not using this. By default, if you are not selecting any register banks, if both are 0, bank 0 will be selected. Is there any overflow? No. This will not be disturbed. And we are not using this one. Since it is an even parity, this will be 0. So this is how the flags will be raised once the given addition operation is done. These are all carries. And that I am writing here. Note on this. Sometimes in the examination, they will give any simple examples stating that show how the flag registers will be affected in PSW register for the following program. They will give the program, so you have to perform addition. After addition, the accumulator will be stored with the value this much. So what is the answer in the accumulator now? The accumulator will be having only 0, 0 because the answer is 0. Okay, the answer is 0, but this is how the flags will be affected. This, make it as important. Sometimes in the examination for 4 marks, they'll ask, show how the flags will be affected in the PSW register, and they'll give simple program. You have to perform addition, and you have to write the PSW register, and how the flags, you have to show the flags. You have any doubts? Now I'll give one more problem. You just solve and show. Tell me how the carriers will be affected. At 3C 3CH with 3CH with 3E. This is an hexadecimal. H represents an hexadecimal number. Now A will be loaded with 3CH. Here A will be loaded with 3C plus 3CH 3BH. Now tell me the answer as well as how the carry flags will be affected. Solve this and tell me the answer. Simply binary addition. What is the answer? What is the answer? And tell me how the flags will be affected. Anyone? Tell me the answer. Are you able to solve or not? Tell me. Simply a binary addition. Suchitra. Who is Suchitra? Manjuna.
Yes, ma'am.
Are you able to solve this?
Yes, ma'am.
What is the answer? What is the answer?
0 1 0
What? Final. Tell me the
0
final
1
answer.
0 0 0.
Anyone else? Have you solved?
B7, ma'am.
Answer is how much?
B7.
7. Can you tell me the flags?
Yes, ma'am.
Tell me.
Yes, ma'am.
Tell me.
AC is auxiliary carry 1, ma'am.
Auxiliary carry is 1. Then
Carry 0, ma'am.
carry 0. Good. Then these two are
0
0.
0.
Selected by 0. What about the parity? Whether it is even parity or odd parity? For even parity it is 0. For odd parity it is 1. Means you have to count number of ones in the result. If they whether they are even or odd.
Even parity, ma'am.
So for even parity you have to write 0. answer is 77. It is not D7. The answer is 77, right? Say yes or no. Is there any auxiliary carry? Yes, there is an auxiliary carry. So you have to write, is there any carry? No, carry is 0. So carry is 0. So count the number of ones. 1, 2, 3, 4, 5, 6. The number of ones are 6. 6 is an even number, so it is even parity. For even parity, it is 0. Correct, no? Take one more as homework. Okay? Take one more program as homework. First you copy this.
Ma'am,
Hmm?
ma'am, can you once again explain this problem, ma'am, please?
Okay. So listen, move A comma hash 3CH. Okay, A will be loaded with the value 3C. We are going to add A with a value 3B because I am loading an immediate value. So A will be already having 3CH. I am going to adding 3B again. So we have to perform binary addition here. So you have to convert this hexadecimals into binary numbers. So 3 means 0011. C means 1100. So similarly 3B 0011 is 3, B is 1011. So perform addition. 01 is 1, 10 is 1, 10 is 1, 11 is 0 carry 1. 1 plus 1 is 0 carry 1. So 1 plus 1 is 0, 1 plus 1 is 0, again you need to add carry 1. So you will be having 1 along with a carry of 1. So similarly 1 plus 1, 1 is carry 1. Then you don't have any values here, directly I am writing 1 here. So you don't have any values here, so 0. You don't have any carry out here. So you need to mark these. This is D7 bit, most significant bit, and this is least significant bit, D0 bit. So for auxiliary carry, I need to check the carry out from first nibble to second nibble. We know that the group of 4 bits is called nibble. Okay, here this is here D1, D2, D3. So if you get any carry from D3 to D4 bit, that is called auxiliary carry. So under those conditions, there exists an auxiliary carry. If exists, you need to write 1. If not, you need to write 0. Clear? And I need to check finally the answer. Answer is 77H. After execution of this particular program, A will be loaded with the value 77H in a hexadecimal number. 77. Clear? And in the results, I need to check how many ones and how many zeros for parity. This is for, in order to check the result, we have to check for parity bit. So now we have to count the number of ones. The number of ones is 1, 2, 3, 4, 5, 6. 6 is an even number, hence it is an even parity. For even parity, we need to write 0. For example, if the result is consisting of, okay, in this we have odd number of ones, 1, 2, 3, 4, 5. Okay, 5 is an odd number. So now the parity is 1. For odd parity we have to write 1. For even parity we have to write 0. Clear?
Yes, ma'am.
Clear, no? Are you able to understand this?
Yes, ma'am.
So now I'll give one more. You have to solve it. Okay? Here, I'll write. So now in the next class you need to add these two and you need to tell how the blacks will be affected in the PSW register. In the next class I will explain about add C and as well as DAA instruction. This is about simply an addition instruction.